Okay, so in this video, we're going to be talking about Newton's first law of motion. This is the first video in Unit 3, which has to do with Newton's laws and forces. And this unit basically has to do with what's called dynamics. The past two units have been kind of the study of what's called kinematics, which studies how objects move, whereas dynamics has more to do with why objects move. Okay, so the different pushes and pulls that causes motion. And so we're going to start off with Newton's first law. We're going to go through all three laws eventually. Okay, but before we get into that, let's cover some basics before we get to Newton's first law. Okay, so first of all, there's some things you just need to know to add to your notes. Now, there's two quantities we're going to be doing a lot of work with. And so here's some information about those two quantities. Now, the first quantity is what's called mass. Mass is basically a measure of how much matter an object is made up of, okay, which essentially has to do with how many atoms make up that object. So all objects are made of atoms, and the mass of an object is basically dependent on how many atoms make up that object. Mass is also a measurement of what's called inertia, and we'll talk more about inertia when we talk about Newton's first law, but basically inertia is the tendency of an object to remain in its current state of motion. Now, the symbol for mass is typically a lowercase, sometimes an uppercase m, okay, for mass. Now, the unit for mass is the kilogram. Now, in chemistry, you might have used the gram for mass. In physics, we use the kilogram just because it's a more, human-sized amount of mass. Okay, so as always, make sure you know the units for things. That really helps you identify givens when you're solving problems. Okay, so we've got mass. By the way, mass is not the same thing as weight, and we'll talk about that momentarily. There is a really important difference between mass and weight that we'll get to in a minute. Okay, but the second quantity you need to know about is what's called force. Now, a force is just a push or a pull. Okay, there's lots of different types of pushes or pulls out there. For example, you've got gravity. Gravity is a force. When you push on somebody or when you pull on a rope, okay, you're exerting a push or pull. Okay, so that is a force. Now, the symbol for force is a capital F, and the unit for force is the Newton, named after Isaac Newton. Newton did a lot of work with forces, and that's why he's got his three laws that everybody knows. Okay, so like I said, force is measured in Newton. So, for example, let's say I have somebody of average weight. They have a mass of 60 kilograms. I might write their mass like this, okay, m equals 60 kg. The mass is 60 kilograms. Let's say I push on an object with, a normal force. I might write capital F equals, 25 newtons. Okay, so that's how I might write that. Subscripts are often used to distinguish different types of forces, and we'll talk about that in the next video. But because there's more than one type of force, we use subscripts to denote different types of forces. And we've kind of seen subscripts before when we talked about velocity. We had VI and V final for initial velocity and final velocity. That's these little letters down here. That's what's called a subscript. We do something similar for forces. Okay, but again, we'll get to that in the next video. Now, one more thing I want to talk about before we get to Newton's first law of motion is I want to talk about the difference between mass and weight. Okay, mass and weight are not the same thing. So, let's go to the next slide. Okay, so what is the difference between mass and weight? Well, there's a couple different differences, and I have included a cute little video for you to watch about the difference between mass and weight. But mass has to do with, I said this before, mass is a measure of inertia. Mass has to do with how much matter makes up an object. Okay, so if, let's say you've got, a box, and your box has some number of atoms that make up that box. Now, if you take your box and you go to, let's say, the moon, your box has the same number of atoms, right? Just because you go from one place to the other doesn't change the number of atoms making up that box. So you would say that the mass of the box is the same on Earth as it is on the moon. Okay, weight is something different. Okay, weight is what we call the force of gravity that acts on an object. Okay, that means weight depends on the pull of gravity from whatever planet or object you're on. So, for example, if you look at this little chart, you can see there's 4 different little people. Each one has a mass of 63.5 kilograms. Okay, you can see, well, actually, it's not 4 different people. It's one person who has the same mass, and it's just showing you that person in 4 different places. So notice on Earth, the Moon, Jupiter, and the Sun, they have the same mass, okay, because they have the same number of atoms no matter where they go. They have the same amount of inertia. They have the same amount of matter, okay. Their weights are different. If you weigh 140 pounds on Earth and you go to the Moon, you only weigh about 23 pounds. On Jupiter, you would weigh about 355 pounds. On the Sun, you would weigh about, 3,914 pounds. And you can, by the way, you can see the weight in newtons. I only tell you the weight in pounds just because you're more familiar with pounds. But weight being a force, it can also be measured in newtons. Any force can be measured in newtons, and weight is a force. Mass is not a force. Okay, so make sure you understand the difference between mass and weight. They're 2 separate things. Again, mass just has to do with how much matter makes up an object. That doesn't change from place to place. In fact, if you take your box into space, it still has the same mass in space. Okay, mass has nothing at all to do with gravity. Weight does, and weight is a force, like I said. Weight is what we call the force of gravity. So, check out this video, and let's go on. This slide basically talks about the difference between mass versus weight again. Mass is a measure of how much matter an object possesses. Weight is a measure of the force that's, pulling the object down because of gravity. Okay, so mass and weight are not the same thing. So you would not say, well, never mind. Mass and weight are not the same thing. Alright, and there is actually an equation for weight, and we're not going to do any calculations in this video, but I do want to tell you the equation to calculate the force of gravity. Now, I should tell you that weight actually depends on the mass of an object, even though they're not the same thing. There is some relationship between mass and weight, and so here it is. The weight of an object, aka the force of gravity, the way we write force of gravity, by the way, is capital F for force, and a subscript G for gravity. And here's the equation for force of gravity, aka the weight. Fg equals m times g. Okay, now, of course, m we saw before is mass, measured in kilograms. G, we've also seen that before. Okay, the force of gravity is equal to the mass of the object times the acceleration due to gravity. And the acceleration due to gravity on Earth, remember, we use a value of negative 10 meters per second squared on Earth, and we've seen that before in past units. Okay, so there is an equation for force of gravity. There it is. Okay, so pause it there if you need to take a look at that. Okay, and this is just like a random chart showing you, how much is a Newton. A refrigerator magnet that weighs 2.3 pounds might weigh 10 newtons. Okay, so Newton is another unit, or the Newton is a unit for force, and force can be measured in pounds, it can be measured in newtons, and so on. So let's get into Newton's first law. Okay, before we get into Newton's first law, let's review. What does it mean for an object to accelerate? Well, hopefully you learned in the first couple of videos that acceleration has to do with how quickly an object's velocity is changing. Okay, so the answer to the question, what does it mean for an object to accelerate? That means the object changes its velocity by definition. Now the second question says, if an object is moving at a constant velocity, what does that imply about the acceleration of the object? Again, hopefully you learned this in the first couple of videos, but an object moving at a constant velocity, by definition, has an acceleration of 0 meters per second squared. Okay, that's just what that means. Alright, now let's get into Newton's first law. And I'm going to break down the first law, but first let's take a look at the first law in its entirety. Okay, so Newton's first law. Here it is. I will try to make it a little bit bigger. The actual first law itself, the way I write it, is down here. I'll try to make the text a little bit bigger so you can see. Maybe like, I don't know, try to make this text a little bit bigger. Alright, so I'm having some issues making it bigger. I don't know why. That's fine. Okay, so here's what Newton's first law says. Let me just back up to how I had it before. Okay, it says, an object at rest will remain at rest, and an object in motion will remain in motion at constant speed in a straight line unless acted upon by net force. Okay, so take a look at that. A lot of people, especially when they're learning about Newton's laws in, let's say, middle school, they always get this wrong. Okay, so I want to make sure that you get this correct. So let me say it again. An object at rest will remain at rest, and an object in motion will remain in motion at constant speed in a straight line unless acted upon by a net force. For some reason in middle school they always leave out the constant speed in a straight line part, which is weird because it's like the most important part. So what does that mean at rest? Well, we know from past units that being at rest means your velocity is 0. You're not moving. Okay, the object is standing still. Okay, so basically it starts off by saying, if an object is not moving, it's going to stay not moving. And an object that is in motion, that means an object that's moving, is going to stay moving. Now, not only is it going to stay moving, but it's going to stay moving in a very specific way. It is going to stay moving at a constant speed in a straight line. Or if you prefer, you can say it's going to stay in motion at constant velocity. Okay, we've heard that term before, constant velocity. Okay, unless acted upon by a net force. So you might ask, what does that mean, net force? We'll talk lots about what net force means. But basically, the first law says either this thing is going to happen or this thing is going to happen unless there's a net force. Okay, so there's two possibilities if there's no net force acting on an object. And again, we'll talk about what a net force is in just a second. But the two possibilities are the object is at rest and it's going to stay at rest, or the object is moving already and it's going to stay moving but only at constant velocity. Okay, those are the only two possibilities if there's no net force acting on an object. And we'll talk about what if there is a net force acting in just a second. Okay, but I like to think of Newton's first law as a flowchart, and so I made this flowchart to show you. But this basically shows you the different outcomes. Okay, so let's say the net force on an object is equal to 0. According to Newton's first law, okay, if an object is at rest, it's going to remain at rest. Or, if the object is in motion, it's going to remain moving at constant velocity. The constant velocity is very, very important. Okay, not only is it going to move, it's going to move in that very specific way. Okay, now, what if the net force on an object is not equal to 0? Well, the only other possibility, besides constant velocity, is that the object is going to accelerate. That means the object is going to change its velocity. The velocity is going to increase or it's going to decrease if the net force is not equal to 0. Okay, so that is basically Newton's first law. Think of it like a flowchart. This would be really good to add this to your notes. Okay, so take a look at that. Okay, so pause there if you need to take more time to look at this flowchart. We're going to do some examples now. Okay, by the way, just to clarify, it's very easy to say Newton's first law, but to actually believe it and understand it is not so simple. Okay, it's actually not so obvious that it's true, because a lot of people think, if you're pushing something, if you stop pushing the object, it's going to stop moving. Okay, so a lot of people think in order for something to move, you have to continue to apply a force, and that's not the case. Okay, that's not what Newton's first law says. The reason people don't fully believe in the first law at first is because normally you have things like friction or air resistance that act on objects in everyday life. Okay, so if you push on the box, if you stop pushing, it's true that the box is going to stop, but only because of friction. Okay, so if you were to push a box on a floor that had no friction, if you stop pushing it all of a sudden, it's not going to stop moving. It's going to keep moving at constant velocity, okay, as long as there's no friction. Okay, so an object cannot change its velocity without a net force acting on it. Okay, but an object does not require a net force to keep moving. So, let's take a look at some examples. I want to show you a simulation really quickly. it's really important that you understand what is meant by net force. Okay, so net force, so we talked about the concept of force before. Force is a push or pull. Net force is basically the total force or the sum of forces acting on an object. Okay, so for example, here is, a tug of war situation. Now, I've got this little blue guy pulling to the left with a force of 50 newtons. By the way, you can also think of that as negative 50 newtons because it's going to the left. Now, if I put a small red guy on the right side pulling to the right, guess what? There's two forces acting on the object, 50 newtons to the left, 50 newtons to the right. I would say that this object has a net force, and I would write net force like this. I would write F, and then I would write net, okay, meaning net force, of 0. Now, how do you get 0 from, 50 newtons and 50 newtons? Because remember, this one is to the left, and the direction matters. Basically, the way you get 0 is you can think we're doing 50 plus negative 50. Okay, and so net force is what you get when you add up all of the forces acting on an object. Okay, so for example, let's say I add another blue guy over here. I'm going to erase this. Okay, now I've got 3 different forces acting on this cart. I've got 50 newtons to the right, another 50 newtons to the right, plus negative 50 newtons to the left. So if I wanted to find the net force, I would just add up all of the forces on the object. I would do 50 newtons plus 50 newtons plus negative 50 newtons, and that would give me 50 newtons overall. Okay, notice my net force is positive, meaning it's going to the right, and so I would say the net force is to the right. If I add another small blue guy, guess what? The net force is going to be 0 now because the 100 and the negative 100 cancel each other out. So that is what is meant by net force. And this is a very, very important concept. Okay, so net force is the sum of the forces. It's what you get when you add up all the forces on an object. Now, this cart is currently at rest. So when I hit go, let's think about what's going to happen because of Newton's first law. Newton's first law says, okay, is the net force 0? Yes. Is the object at rest? Yes. So when I hit go, guess what? The object is going to remain at rest. Seems obvious. Okay. So I'm going to hit pause again. I'm going to add a big blue guy to the left. Notice the net force is now negative 150 because I'm basically adding positive 100 plus negative 250. Okay, this is negative because it's to the left, and I get a net force of negative 150 newtons to the left. So when I hit go here, let's think about what's going to happen in terms of Newton's first law. Newton's first law says, it's going to stay at rest or it's going to move at constant velocity unless there's a net force. Well, guess what? There is a net force. Okay, the net force is to the left. That means this object is going to accelerate. It's going to change its velocity to the left. So when I hit go, I would expect the cart is going to move to the left, plus it's going to speed up. Okay, watch this. And that's what happens. Okay, so let's look at one more situation. I'm going to hit go. So this cart, I'm going to hit pause. This cart is moving. Okay, I hit pause, but it's currently in motion. I'm now going to take off this blue guy so that the net force is now equal to 0 newtons. Okay, now the question is what's going to happen when I hit go? Is it going to, stop moving, or is it going to keep moving? Let's think about Newton's first law. Newton's first law says an object at rest remains at rest, which this is not an object at rest. It's moving, it's just paused. Or an object in motion remains in motion at constant velocity unless acted upon by a net force. And there is no net force here because the net force is equal to 0. So according to Newton's first law, this object should continue to move at constant velocity to the left. Okay, so when I hit go, watch what happens. The cart continues to move with a constant velocity to the left. Okay, just like Newton's first law predicts. Okay, so you can play around with that simulation a little bit on your own later. A few more quick examples. Example 0.5, a bowling ball floating in space has no net force acting on it. By the way, when it says no net force, that's the same thing as writing F net equals 0. Which of the following could describe the motion of the bowling ball? Go back to your Newton's first law flowchart. What does it mean if the net force is equal to 0? Well, it means one of two things. The object is at rest and it's going to remain at rest, or the object is in motion and it's going to remain in motion at constant velocity. Okay, so there's actually two possible types of motion. It could either be A or C. Either it's not moving or it is moving at a constant velocity. By the way, that means if I tell you that the net force on an object is 0, there's no possible way you can tell me is it moving or is it at rest without having more information. Okay, so let's look at a few more examples. Example 1. Try to answer this on your own. The answer is on the next slide, and I'll show you what I put. But try to answer this on your own. While cruising along the highway, you take your foot off the gas and slowly decrease in speed until you stop. According to Newton's first law, what must have happened? Okay, so here's the answer I came up with. In order for your car to slow down, there must have been a net force acting in your car in the opposite direction of motion. Because if you're decreasing in speed, that means you're accelerating. And the only way you can accelerate, according to Newton's first law, is if there's a net force acting on you. Okay, so pause it there if you need to look at that some more. Take a look at example 2. When driving in your car without a seatbelt, you slam on the brakes and your body flies out the window. Explain using Newton's first law why this happens. And I did include a video if you want to check that out. Okay, so pause it there and see if you can answer that question. And here's the answer I came up with. Okay, your car stops because the brakes apply a net force to your car. However, your body experiences no net force, and so it continues to move at a constant velocity through the windshield of the car. Okay, so your brakes don't act on your body, they act on your car. When you step on the brakes and your car stops, your body is supposed to slow down also. Okay, but the only way for that to happen is there has to be a net force on your body slowing it down. That's the purpose of your seatbelt. Okay, without your seatbelt, there's nothing, pushing or pulling on your body telling it to stop. Okay, so that's why you need to wear a seatbelt when you drive in your car. And then one more quick example. A truck is driving down the road at 55 miles per hour when it strikes a concrete wall. A wrench is laying in the back of the truck unsecured. That means it's not tied down. What is the velocity of the wrench immediately after the collision? Explain your answer using Newton's first law of motion. Okay, so pause it there and see if you can figure that out. And here's the answer I came up with. Okay, when the truck stops, the wrench is not tied down, and so there's no net force acting on the wrench. That means it continues to move forward at 55 miles per hour and hits the back of the truck cab, okay, which is not good for your truck, by the way. So, 3 really simple concept problems involving Newton's first law. Newton's first law is not really a calculation law, it's a concept law. Okay, so it's really important that you understand the concept of net force and you understand the concept of this first law flowchart. Okay, so this is definitely something you should add to your notes. So definitely go through these and ask questions if you have any. As always, I will see you guys in the next video.